A simple linear regression, SLR, tries to explain how a response variable y changes when we vary a single predictor x. Think of x as the amount of fertilizer added to a field and y as the crop yield. The model assumes a straight line relationship plus random noise. Y sub I equals beta 0 plus beta 1 x sub I plus epsilon I equals 1, 2 through n. Beta 0 is the intercept, the expected yield when no fertilizer is used. Beta 1 is the slope, how much the yield is expected to increase per unit of fertilizer. Epsilon sub I captures all other influences, weather, pests, and is assumed to have mean 0. The set x sub I, y sub I are the observed data points. By plotting them, we can visually check if they roughly line up, indicating that a linear model might be reasonable. The most common way to find beta 0 and beta 1 is the least squares method. It chooses the line that makes the sum of the squared vertical distances, errors, between the observed y sub I and the predicted y hat sub I equals beta 0 plus beta 1 x sub I as small as possible. The objective function is S of beta 0 comma beta 1 equals sum from I equals 1 to n of opening parenthesis, y sub I minus beta 0 minus beta 1 x sub I closing parenthesis squared. To minimize S, we take partial derivatives with respect to beta 0 and beta 1, set them to 0 and solve. The partial derivative of S with respect to beta 0 equals negative 2 times sum from I equals 1 to n of opening parenthesis, y sub I minus beta 0 minus beta 1 x sub I closing parenthesis equals 0. The partial derivative of S with respect to beta 1 equals negative 2 times sum from I equals 1 to n of x sub I times opening parenthesis, y sub I minus beta 0 minus beta 1 x sub I closing parenthesis equals 0. These give the normal equations. Sum of y sub I equals n times beta 0 plus beta 1 times sum of x sub I. Sum of x sub I y sub I equals beta 0 times sum of x sub I plus beta 1 times sum of x sub I squared. Solving yields the familiar formulas. Beta 1 hat equals the sum of open parenthesis x sub I minus x bar close parenthesis times open parenthesis y sub I minus y bar close parenthesis divided by the sum of open parenthesis x sub I minus x bar close parenthesis squared equals s sub xy divided by s sub Roman 20. Beta 0 hat equals y bar minus beta 1 hat times x bar, where x bar and y bar are sample means. Example, suppose we have data on house size in 1,000 square feet and price in $100,000. The data are size 1.0, price 2.1, size 1.5, price 2.9, size 2.0, price 3.7, size 2.5, price 4.5, size 3.0, price 5.2. Compute x bar equals 2.0, y bar equals 3.68. Calculate s sub xy equals 4.3, and s sub Roman 20 equals 2.5. Then beta 1 hat equals 4.3 divided by 2.5 equals 1.72, and beta 0 hat equals 3.68 minus 1.72 times 2.0 equals 0.24. The fitted line is y hat equals 0.24 plus 1.72x. Explanation. Because the coefficients are computed from random data, we treat beta hat 0 and beta hat 1 as random variables. Under the classical assumptions epsilon iid with mean 0 and variance sigma squared, the estimators have desirable properties. Unbiasedness. E of beta hat 1 equals beta 1 and E of beta hat 0 equals beta 0. Intuitively, on average, the fitted line hits the true line. Variance. Variance of beta hat 1 equals sigma squared divided by the sum of xi minus x bar squared, which equals sigma squared over s sub Roman 20. Variance of beta hat 0 equals sigma squared times the quantity 1 over n plus x bar squared over s sub Roman 20. Larger spread in x, big S sub Roman 20, makes the slope estimate more precise. Covariances. Covariance of beta hat 0 and beta hat 1 equals negative sigma squared times x bar divided by s sub Roman 20. The negative sign reflects that if the intercept is overestimated, the slope tends to be underestimated to keep the fitted line close to the data. Since sigma squared is unknown, we estimate it with mean square error, MSE. Sigma hat squared equals 1 divided by n minus 2 times the sum from I equals 1 to n of y, I minus y hat I squared, which is simply the average of the squared residuals after using up 2 degrees of freedom for the estimated coefficients. Explanation: we often want to know whether the slope or intercept is statistically different from a hypothesized value, typically 0. The t-test does this. Null hypothesis for slope, h sub 0 colon beta 1 equals 0. Test statistic, t equals beta hat 1 minus 0 over square root of var of beta hat 1 equals beta hat 1 over sigma hat times square root of 1 over s sub Roman 20. Under h sub 0, t follows a student's t distribution with n minus 2 degrees of freedom. If absolute t exceeds the critical value from the t-table, or the p-value less than significance level, we reject h sub 0 and conclude the predictor has a real effect. ANOVA, analysis of variance, frames the same test in terms of sums of squares. Total sum of squares SST, sum of y sub I minus y bar squared. Regression sum of squares SSR, sum of y hat sub I minus y bar squared. Error sum of squares SSE, sum of y sub I minus y hat sub I squared. These satisfy SST equals SSR plus SSE. Mean squares, MSR equals SSR divided by 1, and MSE equals SSE divided by n minus 2. The F statistic is F equals MSR divided by MSE with 1 and n minus 2 degrees of freedom. A large F indicates the regression explains a significant portion of variation, equivalently a significant slope. Both the t-test for beta 1 and the f-test are mathematically identical for simple regression, f equals t squared. Explanation: the coefficient of determination, r squared, tells us what fraction of the total variability in y is explained by the regression line. R squared equals SSR over SST equals 1 minus SSC over SST. R squared equals 0 means the line explains nothing. R squared equals 1 means a perfect fit. However, adding more predictors always inflates R squared, even if they are useless. The adjusted R squared penalizes extra variables and is defined as adjusted R squared equals 1 minus SSC over n minus p minus 1, divided by SST over n minus 1. Where p is the number of predictors, p equals 1 for simple regression. Adjusted R squared can decrease if a new variable does not improve the model sufficiently. Example: continuing the house size data. SST equals the sum of yi minus y bar squared equals 4.736. SSR equals the sum of y hat I minus y bar squared equals 4.534. SSE equals 0.202. Thus R squared equals 4.534 divided by 4.736 equals 0.957. 96% of price variation is explained by size. Adjusted R squared equals 1 minus 0.202 divided by 3 divided by 4.736 divided by 4 equals 0.951, only slightly lower because we have only one predictor. High R squared is encouraging, but we must still check assumptions and residuals. Explanation: a regression model not only gives point predictions but also intervals that reflect uncertainty. Number 1, confidence interval for the mean response at a particular x0. Y hat 0 equals beta hat 0 plus beta hat 1 x0. CI mean, y hat 0 plus minus t alpha over 2 n minus 2 sigma hat square root of 1 over n plus x0 minus x bar squared over s Roman 20. This interval tells us where the average price of houses of size x0 is likely to lie. Number 2, prediction interval for a new observation at x0. Prediction interval: y hat 0 plus minus t alpha over 2 n minus 2 sigma hat square root of 1 plus 1 over n plus x0 minus x bar squared over s Roman 20. The extra 1 under the square root inflates the interval because a single future house will also have its own random error epsilon. Numerical illustration: using the house example, suppose we want the price for a 2.2 thousand square foot house x0 equals 2.2. Compute y hat 0 equals 0.24 plus 1.72 times 2.2 equals 3.99. Let sigma hat equals square root of SSE over n minus 2 equals square root of 0.202 over 3 equals 0.259. With n equals 5, x bar equals 2.0, s Roman 20 equals 2.5, and t 0.0253 equals 3.182. Standard error for mean equals 0.259 times square root of 1 over 5 plus 2.2 minus 2.0 squared over 2.5 equals 0.259 times square root of 0.2 plus 0.016 equals 0.259 times 0.466 equals 0.121. Confidence interval for mean 3.99 plus minus 3.182 times 0.121 equals 3.99 plus minus 0.385 equals 3.605 to 4.375. Standard error for prediction equals 0.259 times square root of 1 plus 0.2 plus 0.016 equals 0.259 times square root of 1.216 equals 0.259 times 1.103 equals 0.286. Prediction interval 3.99 plus minus 3.182 times 0.286 equals 3.99 plus minus 0.910 equals 3.08 to 4.90. The prediction interval is wider because it also accounts for the random error of a single future house. Linear regression rests on several key assumptions. If they fail, the estimates may be biased or inefficient. Linearity, the true relationship between y and x, is straight. Plot residuals E sub I equals y sub I minus y hat sub I versus x sub I. Look for patterns curves that indicate non-linearly. Independence, errors for different observations are unrelated. In time series data, plot residuals against time. Use Durbin-Watson test for autocorrelation. Homoscedasticity, errors have constant variance sigma squared. Plot residuals versus fitted values. A funnel shape signals heteroscedasticity. Normality, errors follow a normal distribution needed for exact T over F tests. Histogram or QQ plot of residuals. Apply Shapiro-Wilk test. No exact multicollinearity only matters for multiple regression. Diagnostic steps. 1. Residual versus fitted plot. Randomness suggests linearity and homoscedasticity. 2. Scale location plot square root of standardized residuals versus fitted, checks variance stability. 3. Normal QQ plot, points should lie on a straight line. 4. Leverage and influence. Cook's distance identifies observations that disproportionately affect coefficients. If assumptions are violated, remedies include dash transform y log square root to stabilize variance. Dash adding polynomial terms or using nonlinear models for curvature. Dash using weighted least squares for heteroscedasticity. Dash applying robust regression methods. Regular diagnostic checking is a vital part of any regression analysis, not an afterthought. Explanation : below are typical exam-type questions that test understanding and ability to apply the concepts. 1. Derivation question : given data open parenthesis x sub I comma y sub I close parenthesis for I equals 1 to n comma derive the least squares estimators beta hat 0 and beta hat 1 period show each step of the calculus. Students write the sum of squares, take partial derivatives, set to 0, solve the normal equations. 2. Computation question : the following table gives the number of hours studied x and exam score y for 6 students. Compute beta hat 0, beta hat 1, r squared, and provide a 95% confidence interval for the slope. Use t sub 0.025, 4. 3. Hypothesis test : test at the 5% level whether the slope is 0. State the null and alternative hypotheses, compute the test statistic, and interpret the p-value. 4. ANOVA table : construct a full ANOVA table open parenthesis source. Degrees of freedom, sum of squares, mean square, f close parenthesis for the regression in question 2 and state the conclusion. 5. Confidence and prediction intervals : using the regression from question 2, find a 99% confidence interval for the mean score when a student studies 8 hours, and a 99% prediction interval for a future student studying 8 hours. 6. Diagnostics: given a residual versus fitted plot that shows a clear U shape, Discuss which assumption is violated and propose a remedy. 7. Conceptual: explain why adjusted R² can be lower than R² and why it is preferable when comparing models with different numbers of predictors. 8. Real-world modeling: a civil engineer models the deflection d of a beam in millimeters as a function of load L in kilonewtons using simple linear regression. The data show a strong curvature. Suggest 2 alternative modeling strategies and justify them. When solving these problems, students should show all algebraic steps, no skipping calculus. Clearly label each quantity SSR, SSE, etc. Interpret results in the context of the example. For example, each additional hour of study increases the expected score by 2.3. Comment on assumptions before drawing conclusions. Practicing such questions builds the ability to move from theory to practical engineering decisions.